Hello students, very good morning. So today's session we will discuss a physical chemistry topic that is the topic is solid state. The subtopic is band theory of solids. Okay. So this is a very important topic for entrance examination point of view. So most probably here the question asking in the area of types of semiconductors, that is N-type and P-type. So means in N-type semiconductors, the levels means the forbidden energy gap is nearer to which band, and also in P-type semiconductor, the forbidden energy band is nearer to which band. So these type of questions are asking in the entrance examination point of view. So we will move to the topic, student. Right. So band theory of solids. This theory was proposed by Sommerfeld and Bloch. Okay, Sommerfeld and Bloch. According to this theory, means what is mean by a band? Band means nothing but, student, a set of closely spaced energy levels. So means the energy levels are come closer or nearer. So then it form a band, or it means it is a continuous energy levels. The energy gap between the lower and higher energy level are very small. So it is we can imagine it is means in a band the 10 to the power of 23 energy levels are closely energy levels are there. So we can call it as a band. According to this theory, the entire metal is related. Entire metal is treated as a big molecule. The entire metal is covered by molecular orbital. Okay. For example, here we will take an example like lithium or sodium metal is having one 3s electron in that lithium metal. So we have only one 2s orbital is available for forming bonding molecular orbital. So this is the valency electron. Here you can see the electronic configuration, that is 1s2, 2s2, 2p6, 3s1. So this is the 3s orbital. So this is outer electron, or we can call it is valency electron. This 3s1 electron is a delocalized electron, that is, it belongs to all the sodium atoms present in the solid. This leads to applicability of molecular orbital. So this is a valency electron. So this electron is causes for the conductivity in the sodium metal. Here you can see this is the sodium metal, and it is the nucleus with positively charged, and this is 1s electron, 1s2, and this is a 2s2 and 2p6, and this is 3s1. So this 3s1 electron is a valency electron. It is far away from the nucleus, and this electron is easy to reduce, and it electron is easy to donate, and it easy to free to move from the excited state. So then it causes conductivity in metals, right? Here you can see we have a set of sodium metals of their energy levels. Here you can see. So here you can take, this is a single sodium atom, student. So this is a single sodium atom. So this is 1s, this is 1s2, 2s2, and this is 2p6 and 3s1. So for a single sodium atom, here you can see when the sodium atoms are merged, or means the atomic orbital of sodium, then it forms a molecular orbital. So this is a bonding, one is bonding molecular orbital, and this is anti-bonding molecular orbital. Here the energy gap between these one is lesser compared to the first sodium atom. So this is 2s sigma 2s and sigma star 2s sigma 2p, and this is means 2p sigma 2p and pi 2p like this, and this is 3s1 molecular orbital. Okay, one is bonding molecular orbital and another one is anti-bonding molecular. And here you can, we are taking one more sodium atom is increases right here. The three sodium atoms are combined. So here you can see the energy between these energy levels are comes, or as the number of atoms going on increases, the energy levels are, the energy gap between from one to another will be decreases. So far, student, as the number of sodium atom here, n number of sodium atom will be present, n number of sodium atoms will be present. So the energy gap is means nothing but here 10 to the power of 23 atoms, like. So means the 10 to the power of 23 atoms we can't imagine. So here these energy gaps are very close to each other. So then we can say, so this continuous energy levels quanta means this is these quasi continuous energy levels we can called as a band. We can called as this is 1s band, 2s band, 2p band and 3s band. So these continuous energy levels are we can called as bands. Okay. So what is happen in this band? So this free 3s electron is moved to this energy level. So then it conducts the conductivity in metals. So it shows conductivity property. So therefore the metal shows conductivity. So because these valency electrons are excited from one level to another level, that is conductors, we can say conductors, right? Here you can say what is mean by a conductor? The metals are conductors in which there is no forbidden energy gap between the conduction band and valency band. So means here in conductors the valency bond and conduction band. The valency bond is the lower and conduction band is the higher. So there is no forbidden energy gap. So means the electrons are easily jumps from valency band to conduction band. They exhibit the conductivity property in metal. So mean there is no need to provide any extra energy is required to transfer the electron from VB to CB. Right? Here you can see this is the energy graph. We are plotting energy, potential energy. Here this is the valency bond and here this is the conduction band. So the electron, there is no forbidden energy gap. So therefore the electrons are easily moved from valency band to conduction band. So therefore the metals are shows conductivity property in nature, right? Next, so in semiconductors the energy gap is little bit more, means we can say it is higher than conductors and lower than insulators. Okay, here you can see the band energy gap in the semiconductors, but in the insulators the energy gap is very high. So means if we provide any kind of energy, the valency electrons cannot be excited. Excitation is cannot takes place into the conduction band. So therefore generally the insulators cannot allow the current or cannot be allowed current through them. So then we can say the materials are called as insulators. Okay, here the energy gap is very high. The forbidden energy gap is very high in insulators. But in semiconductors the forbidden energy gap is um, lower than insulators and greater than conductors. Then we can say it is a semiconductors, right? Here you can see the band gap. What is mean by a semiconductor? In semiconductor the valence band is completely filled with the electrons while conduction band is empty. So there is energy gap between the band is less. For therefore the electron jumps from valency band to conduction band at room temperature. Okay, so need to be maintained. If the temperature is 0, so there is no transfer of electrons from the valency band to conduction band. So means what is says student, in semiconductors at 0 degrees temperature, 0 Kelvin temperature, so generally the semiconductors cannot exhibit the conductivity property. As the temperature means the temperature is increases, means it reaches room temperature, it shows low conductivity. When the temperature is going on increases, generally the semiconductors exhibit the conductivity property. But the in the valency bond, so generally the energy gap is very high. So therefore the electron cannot be jumped from valency band to conduction band. So hence they cannot exhibit the conductivity property, right? So in insulators, the valency band is completely filled while the conduction band is empty. So these results a large energy gap, since the energy gap between the conduction band and the valency band is more. So there is no movement of electron from the valency band to the conduction band. So that is in the case of insulators, right? So then we will move to the temperature. This is a very important. The temperature effect on conductors, semiconductors and insulators, right? So effect of temperature. In conductors, with increase in temperature, the conductivity decreases. because as the temperature increases, the velocity of electrons increases and the direction of electron charge carriers get cancelled by each other, hence the conductivity decreases. Means the charge, when the electrons are moving randomly, so therefore the charge is cancelled by each other, so therefore the conductivity decreases in conductors. Okay, in semiconductors, with the increase of temperature, the conductivity also increases, because as the temperature increases, the electron charge carriers from valence band to conduction band, right? Here at low temp, at 0 degrees Kelvin, at 0 Kelvin degrees, the semiconductors cannot exhibit the conductivity property. At room temperature, it shows the low conductivity. While we are increasing the temperature, so therefore the moving of electrons takes place from valence band to conduction band. They can exhibit the conductivity property at the temperature going on increases, right? But in insulators, the increase in temperature decrease the forbidden energy gap. That is very, very important. So means the energy gap is decreases when the temperature increases to some extent and starts conduction. Hence, at some temperature, insulator behave as the conductor. With the increase in temperature, the conductivity of the insulators increases and the resistance is decreases, because the conductivity is always inversely proportionality to the resistance. If the conductivity increases in insulators, the resistance will be decreases, right? So this is about effect of temperature in conductors, semiconductors and insulators. Student, is that clear, student? Right. Next, in intrinsic semiconductors, so generally the semiconductors are classified into two types, that is intrinsic semiconductors and extrinsic semiconductors. So what is mean by a intrinsic semiconductor? So intrinsic semiconductors means nothing but the pure silicon and germanium semiconductors. We can say it is intrinsic semiconductors, right? The pure silicon and germanium are called as intrinsic semiconductor, students, right? The conductivity increases, the conductivity of intrinsic semiconductor increases with temperature. That is very, very important. In the solid state of each silicon and germanium is bonded to 4 silicon and germanium atom by the electrocovalent bond. At low temperature, silicon and germanium are bad conductors, but at room temperature shows low conductivity. While the temperature increases, the conductivity is increases, right? So generally, the energy gap of silicon is 1.1, the band gap is 1.1 electron volt. In germanium, so that is 0.72 electron volt. So means when we applied, so when we supply 0.72 electron volt, so means the electron jumps from the valence band to conduction band, right? So this is a intrinsic semiconductor. So this is the pure semiconductor. So the each silicon atom, you can take germanium atom also. The each silicon atom is attached with 4 silicon atom, means which is it forms a covalent bond and it is shows octet rule also. Okay, so this is the covalent bond, this is the covalent bond, this is the covalent, and so means here, so each silicon atom has 4 valency electron. So therefore these 4 valency electrons can bound with the neighboring 4 silicon atoms and forms a silicon, forms a intrinsic semiconductor, right? So in this intrinsic semiconductors, the forbidden energy gap is exactly mid from the valency band and conduction band. So it is not nearer to the valency band and it is not nearer to the conduction band. It is near, it is a completely mid region of valency band and conduction band. Here you can see, so this is the forbidden energy band. So this is, we can say, FB energy band, FB energy band. So this is half to the conduction band, half to the valency bond. So this is about intrinsic semiconductor, student. Is that clear? Right. Next, we will move to the extrinsic semiconductor, right? So definition of extrinsic semiconductor, right? Extrinsic semiconductors are those that are that the result of adding impurity, right? So what is mean by, student? We are adding impurities to the pure semiconductor. That means pure silicon and pure germanium semiconductors. We are adding impurities of like third group elements and fifth group element, so to increase the conductivity property. Okay, the intrinsic semiconductors at room temperature shows low conductivity. At 0 kelvins it cannot shows the conductivity property. While we are adding impurities, or we can say it is doping, then it exhibit the semiconductivity, it shows the conductivity property. Okay, right. So here the process by which certain amount of impurity is provided or added to pure semiconductor is known as, we can say, it is doping. So we can say a pure semiconductor is doped to generate an extrinsic semiconductor, right? So there are highly conductivity in nature. So means extrinsic semiconductors shows high conductivity in nature. Extrinsic semiconductors are two types. One is p-type semiconductor and another one is n-type semiconductor. It is not worthy here that the classification of that extrinsic semiconductor depend upon the type of element doped to the pure semiconductor. That is a very important, right? Here you can say, then we will move to the n-type semiconductor. N-type semiconductor, when one of the silicon atom is replaced by the fifth group element like arsenic or stibine, the following structure results. One of the electron of arsenic is free. So this free electron occupy a discrete level that is found to lie about 0.1 electron volt below the conduction band. Here you can see. So these decreased energy levels acts as donor levels because the electrons them of sufficient energy to get the conduction band. Here, so I'll explain here in this structure. Here you can see, so one of the silicon atom is replaced by arsenic. So therefore, arsenic is a pentavalent. So means 5 valency electrons are there. So these 5 valency electrons can form the 4 covalent bond with the 4 neighboring silicon atom, but one free electron is left over in this interstitial space. So this free electron means not only one silicon. So here we number of arsenic or arsenic elements are there. So therefore these free electrons can cause conductivity in these n-type semiconductors, right? So these free electrons can create conductivity property in n-type semiconductor, right? So in this n-type semiconductor, student, so then we can say these free electrons we can call as a donor electrons, or we can call it as donor level. So here you can see, so this is a valency bond and conduction band. So in this extrinsic semiconductor of n-type, so this is a donor energy level, or we can call it as it is a forbidden energy gap, or FB band, forbidden band. So forbidden band is very nearer to the conduction band. It is very important. Many of times the question was framed from this type, right? So here the forbidden band is nearer to the conduction band in n-type semiconductor. That is very, very important, right? So these free electrons, so means these decreased energy level acts as donor levels because electrons them of sufficient energy to get conduction band. So means here these free electrons are moved towards the conduction band. So therefore the forbidden energy band move towards the conduction band. So clear, student, right? Next, so p-type semiconductor, right? So when one of the silicon atom is replaced by the third group element like gallium or you can aluminum. So one of the gallium silicon bond is electron deficient, and following the structure detail results. You can, according to the band theory, the energy levels associated with a single electron silicon and gamma gallium bond does not form in the part of valency band, but it forms a discrete level just 0.1 electron above that valency band. So these levels are known as acceptor levels. In that p-type n-type semiconductor we can call it as a donor levels. These are we can call it as acceptor levels. Clear, student, right? So the electrons from the valency band may have sufficient energy, may be promoted to acceptor level so it create a hole in the valency bond. So these hole are we can call as a positive holes in the valency bond are able to move freely. Right here you can see this is the p-type semiconductor. So the gallium is a third group element. So it has three valency electrons only, right? So these three valency electrons can form three covalent bond with the neighboring silicon atom. But here, so this is create a hole in this interstitial space, right? So these free electron, so what it causes, right? So for example, so this electron move to here, so means it this electron move to here, so then here, so it creates a hole. So this another type, here you can see this electron is moved to here, it create hole. So means here, so these number of holes in the valency bond are able to move freely. So therefore these positive holes can causes conductivity in p-type semiconductors. Clear, student? Right, here you can see this is the valency bond and the conduction band. So here you can see, so the forbidden energy band is nearer to the valency band. That is a very important, right? In n-type semiconductor, the forbidden energy band we are calling as a donor level, it is nearer to the conduction band. But in p-type semiconductor, the it is the forbidden energy band we are calling as acceptor band. So it is nearer to the valency band. So this is about the band theory of solids in solid state chemistry. So this is a physical chemistry topic, student. I hope so you understood. Thank you.